You're wrong about time travel. Not in the way you think. Time travel isn't some science fiction fantasy that requires wormholes or flux capacitors or breaking the laws of physics. Einstein proved it's real over a century ago. And he did it with a thought experiment so simple it involves just two people, identical twins, and yet so paradoxical that it confused some of the brightest physicists for decades. Here's the story. Imagine two twins. Let's call them Alice and Bob. They're born on the same day, same hospital, same minute, identical in every way. Now, when they turn 25, Bob decides he wants to be an astronaut. He boards a spacecraft capable of traveling at 90% the speed of light, and he takes off into deep space. Alice stays home on Earth. She lives her normal life, gets a job, maybe gets a dog, watches Netflix, whatever. Bob, meanwhile, is out there in his spacecraft, zooming through the cosmos at nearly 300,000 kilometers per second. After what feels to him like 5 years of travel, he turns around and comes home at the same incredible speed. Bob lands back on Earth, excited to see his twin sister. He's been gone for what felt like 10 years to him, 5 years out, 5 years back. He's now 35 years old. But here's the twist that breaks your brain. When Bob steps out of his spacecraft, Alice is 70 years old. Bob has time traveled into the future, not metaphorically. Actually, he's experienced 10 years while his twin sister experienced 45 years. Bob is biologically, physically, objectively younger than his identical twin. His cells have divided fewer times. His heart has beaten fewer beats. He has literally aged less. This isn't science fiction. This is Einstein's theory of special relativity. And it's been proven experimentally over and over again. We'll talk about those experiments later, but for now, just sit with how absurd this sounds. How can one twin age slower than the other, just by moving really fast? But here's where it gets even weirder, where the paradox emerges. Because from Bob's perspective, inside that spacecraft, he wasn't moving at all. He was just sitting there in his captain's chair, and it was Earth that was moving away from him at 90% the speed of light. If motion is relative, which Einstein says it is, then shouldn't Alice be the one who aged slower? Shouldn't Bob be the 70-year-old when he gets home? Both twins think the other one is moving. Both twins should think the other one's clock is running slow. So who's right? How can Bob be younger and Alice be younger at the same time? That's impossible. That's a logical contradiction. That's the paradox. This paradox, the twin paradox as it's called, stumped people for years. Some physicists thought it proved Einstein was wrong. Others thought it was a trick question. Einstein himself had to clarify the answer multiple times. And the resolution, it's so elegant, so beautiful, so mind-bending, that when you finally understand it, you never think about time the same way again. So, buckle up. We're about to break your intuition about what time even is. We're going to dismantle everything you thought you knew about clocks and aging and the flow of the universe. And by the end of this video, you're going to understand one of the deepest truths about reality that Einstein ever discovered. Let's start with the basics. What is time really? Before Einstein came along, everyone thought they knew what time was. Time is time, right? It flows forward at the same rate for everyone, everywhere. A second on Earth is a second on Mars is a second in a distant galaxy. Clocks might break or run fast or slow, but that's because they're badly made. Real time, absolute time, universal time that just marches on, independent of anything we do. Isaac Newton believed this. He wrote about absolute, true, and mathematical time that flows without relation to anything external. In Newton's universe, you could imagine a giant cosmic clock somewhere out in space ticking away, and everyone's watches could theoretically synchronize to it. If you're on Earth and I'm on a spaceship, we might disagree about distances or speeds, but we'd agree on what time it is. Einstein said, nope, that's completely wrong. Here's the thing that breaks most people's brains immediately. Time is not absolute. Time is not universal. Time is not the same for everyone. Time depends on how you're moving. Let me give you an everyday example that doesn't quite capture relativity but starts to build the intuition. Imagine you're standing still on a sidewalk and your friend is on a train moving past you at 60 miles per hour. You throw a ball forward at 20 miles per hour relative to you. How fast is that ball moving? To you, standing still, it's moving 20 miles per hour. Simple. But to your friend on the train, that ball is moving, well, it depends which direction they're going. If they're moving the same direction as the ball looks like it's moving slower. If they're moving the opposite direction, the ball looks like it's moving faster. Velocity is relative to the observer. Okay, you say, sure, velocity is relative, but time? Time should still be the same for both of us, right? Wrong. And here's why Einstein realized time had to be relative too. Light is weird. Light travels at exactly 299,792,458 meters per second in a vacuum. Every single experiment we've ever done confirms this. But here's the kicker. Light travels at that speed for everyone, regardless of how they're moving. Read that again because it's bonkers. If you're standing still and shine a flashlight, the light travels at light speed. If you're in a spaceship going 90% of light speed and you shine a flashlight forward, the light doesn't go 1.9 times light speed. It still goes exactly light speed. If someone standing still measures that beam of light from your moving spaceship, they also measure it going exactly light speed. How is that possible? How can light travel at the same speed for everyone, even if we're moving relative to each other? Einstein realized there's only one way this works. Time itself must stretch and squeeze depending on your motion. Imagine you're on that spaceship and you have a light clock, literally just a beam of light bouncing between two mirrors 1 meter apart. Each bounce is a tick of the clock. To you, sitting still in the spaceship, the light just goes straight up and down. Tick, tock, tick, tock. 1 meter up, 1 meter down. But now imagine I'm standing still on Earth, watching your spaceship zoom by at 90% light speed. From my perspective, that beam of light isn't just going up and down, it's also moving sideways because the whole spaceship is moving. So the light has to travel a longer path. It's going diagonally, up and to the right, down and to the right. The light traces out a zigzag pattern from my point of view. But here's the thing. Light still travels at the same speed for both of us. It has to. That's the law of the universe. So, if the light in your clock is traveling a longer path from my perspective, but moving at the same speed, then it must take longer to make each bounce. Your clock, from my perspective, is running slow. This isn't because your clock is broken. This is because time itself is running slower for you. Your heartbeats are slower. Your thoughts are slower. Your aging is slower. Everything about time in your frame of reference is dilated, stretched out when viewed from mine. This is time dilation. And it's real. It's not a trick. It's not an optical illusion. It's a fundamental feature of reality. And this is where the paradox begins to creep in. Because if I'm watching you move and your clock runs slow, what do you see when you watch me? Let's go back to Alice and Bob, our twins. Bob gets in his spaceship and accelerates away from Earth at close to the speed of light. Alice stays home. From Alice's perspective on Earth, she watches Bob's spaceship receding into the distance. Bob is moving relative to her. And according to time dilation, moving clocks run slow. So, from Alice's point of view, Bob's clock and Bob's heartbeat and Bob's entire life is happening in slow motion. She sees Bob aging slower than she is. If Alice could somehow watch Bob through a super telescope, she'd see him moving sluggishly. If Bob waves at her once per second by his count, she might see him wave only once every 2 seconds, or 5 seconds, or more, depending on exactly how fast he's going. Bob's time is dilated relative to Alice. This is exactly what Einstein's equations predict. So after 10 years pass on Bob's clock, 5 years out, 5 years back, way more than 10 years have passed for Alice, maybe 45 years. When Bob returns, he's younger. Time travel. Boom. Makes sense, right? But here's the twist that makes this a paradox. From Bob's perspective, sitting in his spaceship, he's not moving at all. Think about it. When you're sitting in a car on the highway, you don't feel like you're moving. You feel stationary, and the landscape moves past you. There's no absolute state of motion in the universe. All motion is relative. So, from Bob's point of view, he's sitting still in his spacecraft, minding his own business, and it's Earth that's moving. It's Alice who's receding into the distance at 90% the speed of light. And if moving clocks run slow, then from Bob's perspective, it's Alice's clock that should be running slow. It's Alice who should be aging in slow motion. Do you see the problem? Alice thinks Bob's clock is running slow. Bob thinks Alice's clock is running slow. They can't both be right. When Bob gets back to Earth, either Bob is younger, or Alice is younger, or they're the same age. But they can't simultaneously both be younger than each other. That's logically impossible. This is the twin paradox. And when Einstein first published special relativity in 1905, people immediately started arguing about this. Some said it proved the theory was self-contradictory. Others said there must be some hidden assumption. Some thought the whole thing was nonsense. Let me make the paradox even sharper. Imagine during Bob's journey, both twins are constantly watching each other through telescopes and sending light signals back and forth. Alice, watching Bob leave, sees his clock ticking slowly. She sends him a signal every year, according to her clock. Bob receives these signals, but because of the relativistic effects, they seem to arrive slowly from his perspective because Alice's clock is running slow from his view. Bob, watching Alice recede, sees her clock ticking slowly. He sends her a signal every year according to his clock. Alice receives these signals, but they arrive slowly from her perspective because Bob's clock is running slow from her view. Each twin literally sees the other twin's clock running slow. This is real. This is what they observe. So when they reunite, who aged less? Your intuition screams that this should be symmetric. If Alice sees Bob aging slowly, and Bob sees Alice aging slowly, they should age the same amount. The situation looks identical from each perspective. How can one twin definitively be younger? But experiments prove Bob is younger. We know this. We've tested it with atomic clocks on airplanes. We've tested it with particles in accelerators. The traveling twin always comes back younger. Always. So, what breaks the symmetry? What's different about Bob's experience compared to Alice's? This is where people get stuck. Some give up and say, well, relativity is just weird, I guess. But that's not satisfying. There has to be a reason. There has to be something different about Bob's journey that makes him the younger twin. And there is. Or there absolutely is. But the answer is subtle. It requires us to think more carefully about what we mean by perspective and time and symmetry. Here's a hint before we dive into the resolution. The situation is not actually symmetric. Alice and Bob do not have equivalent experiences. And the difference has to do with something Bob does that Alice doesn't. Bob accelerates, Bob turns around, Bob changes his velocity. Alice never does. Alice stays in one inertial reference frame the entire time, a frame that's not accelerating, not changing velocity. Bob, on the other hand, has to fire his rockets to speed up, then fire them again to slow down and turn around, then fire them again to speed up back toward Earth, then fire them one last time to slow down and land. But here's the question. Does acceleration really break the symmetry? Why should turning around make Bob's experience fundamentally different from Alice's? Some people say, well, Bob feels the acceleration. He's pushed back in his seat. He feels the G-forces. That makes his frame non-inertial. And special relativity only applies to inertial frames, so the symmetry breaks. That's kind of true, but it's not a satisfying explanation. It sounds like a technicality. It doesn't tell us what's really happening with time. So let me give you the real resolution, the one that makes everything click into place. the one that shows you what time actually is in Einstein's universe. Here's the key insight that resolves the paradox. Time is not some invisible river flowing through the universe. Time is a dimension like space. And the amount of time you experience depends on the path you take through space-time. Let me explain that with an analogy that doesn't involve time at all, just space. Imagine Alice and Bob are both in New York City, standing on the corner of Fifth Avenue and 42nd Street. They both want to get to the corner of Fifth Avenue and 52nd Street, 10 blocks north. Alice walks straight north, 10 blocks straight line. If each block is 100 meters, she walks 1,000 meters total. Her pedometer reads 1,000 meters. Bob decides to be creative. He walks 5 blocks east, 10 blocks north, then 5 blocks west, arriving at the exact same destination as Alice. Bob's pedometer reads, well, 5 blocks plus 10 blocks plus 5 blocks equals 20 blocks equals 2,000 meters. They both started at the same point. They both ended at the same point, but they traveled different distances. Bob's path through space was longer. His odometer, his pedometer clicked over more times than Alice's. Nobody finds this paradoxical. Of course, different paths through space can have different lengths. That's just geometry. Now here's the mind-bending part. The same thing happens with time. Different paths through space-time have different lengths. And the length of your path through space-time is the amount of time you experience what physicists call proper time. Alice stays on Earth in space-time, which is a 4-dimensional thing combining 3 dimensions of space and 1 of time. Alice's path is almost straight through the time dimension. She's not moving much through space, so her path is primarily just advancing through time. Her space-time odometer, her clock, accumulates lots of ticks. Bob travels out and back at high speed. His path through space-time is different. He's moving a lot through the space dimensions, which means, and this is the weird part, his path is actually shorter through the time dimension. His space-time odometer, his clock, accumulates fewer ticks. They both start at the same space-time event, Earth 2025, the moment Bob leaves, and both end at the same space-time event, Earth 2070, the moment Bob returns. But Bob's path between those events is shorter in terms of proper time. His clock experiences less time. He ages less. This isn't symmetric. Just like in the walking analogy, one path can be straight and short, while another path can be curved and long, or in space-time. One path can be straight and long in proper time, while another can be curved and short in proper time. But wait, you ask, why does moving through space reduce your movement through time? Why can't you move fast through both? Because of the speed of light. Everything in the universe is always moving through space-time at exactly the speed of light. Always. You, me, every particle, every object. We're all moving through space-time at light speed. Right now, sitting still in your chair, you're moving through time at maximum speed, 1 second per second. You're not moving through space, so all your motion is through time. But if you start moving through space, if you get up and walk or drive or fly in a rocket, then some of your motion through space-time gets diverted into the space dimension. And that means less motion through the time dimension. Your clock ticks slower. The faster you move through space, the slower you move through time. At the extreme, if you could move through space at light speed, which you can't, but light itself does, you wouldn't move through time at all. Photons don't experience time. From a photon's perspective, it's emitted and absorbed in the same instant, even if it travels across the universe. Bob moves very fast through space, so he moves slowly through time. Alice doesn't move much through space, so she moves quickly through time. When they reunite, Bob has experienced less proper time, he's younger. Now let's address the symmetry concern more carefully. Yes, Bob sees Alice moving away. Yes, from Bob's instantaneous reference frame at any given moment, Alice's clock does appear to run slow. But here's the crucial point. Bob doesn't stay in one reference frame for the whole journey. When Bob accelerates to turn around, when he fires his rockets to change direction, he changes reference frame. And when you change reference frames in special relativity, what you call now changes. Your definition of simultaneity changes. Imagine Bob is halfway to his destination, and he's 5 light years away from Earth. And according to his clock, 5 years have passed. He looks back at Earth through his telescope and asks, what's happening on Earth right now? In his current reference frame, moving away from Earth, right now on Earth might mean only 6 years have passed there. So Alice is just slightly older than him. Makes sense. But then Bob fires his rockets. He decelerates, turns around, and accelerates back toward Earth. He's now in a different reference frame, one moving toward Earth instead of away from it. And in this new reference frame, his definition of right now on Earth suddenly jumps forward. Right now on Earth might suddenly mean 39 years have passed there. Bob's turnaround causes him to skip forward in what he considers to be simultaneous with his experience. Alice doesn't have this discontinuity. Alice's notion of now evolves smoothly and consistently. Bob's jumps when he accelerates, that's the asymmetry. That's what breaks the apparent paradox. Bob's journey involves changing reference frames. Alice's doesn't. Another way to think about it, if we include a third observer, let's say Carol, who flies past Earth at constant velocity in the same direction Bob eventually goes, and keeps going forever without turning around, Carol would see Alice aging quickly and Bob aging slowly while he's moving away. But Carol would also see Bob aging slowly on his way back. From Carol's single, consistent inertial reference frame, there's no paradox at all. Bob's clock just runs slow the whole time because he's moving relative to Carol. The paradox only appears when Bob tries to compare his rate of aging to Alice's from his own perspective. And the resolution is that Bob doesn't have a single, consistent perspective. He jumps between perspectives when he accelerates. The bottom line, different paths through space-time have different proper time lengths. Bob took a path with shorter proper time. He aged less. No paradox. Now, you might be thinking, this is all very clever mathematical reasoning, but does this actually happen? Is this real or just some theoretical curiosity? It's real. Incredibly, impossibly, undeniably real. In 1971, physicists Joseph Hafele and Richard Keating put atomic clocks, the most precise timekeepers humans have ever built, on commercial airplanes and flew them around the world. When they compared these clocks to identical clocks that stayed on the ground, the flying clocks had aged less, by nanoseconds, yes, but measurably less. The planes didn't travel near light speed, just 500 miles per hour, so the effect was tiny, but it was there, exactly as Einstein predicted. Cosmic ray muons give us an even more dramatic example. Muons are unstable particles created when cosmic rays hit the upper atmosphere. They decay in about 2 microseconds. At the speeds they travel close to light speed, they should only make it about 600 meters before decaying. But we detect them at sea level, which means they traveled over 10 kilometers. How? Time dilation. From our perspective, their clocks run slow, so they last longer. From their perspective, the distance is contracted. Either way, they make it to the surface because of relativity. GPS satellites have to account for time dilation every single day. They're moving fast relative to us on the ground. So special relativity says their clocks should run slow, but they're also higher in Earth's gravitational field. So general relativity says their clocks should run fast. Engineers have to correct for both effects, or GPS would drift by kilometers per day. Your phone's map app works because Einstein was right about time. And here's my favorite. NASA actually had twin astronauts, Scott and Mark Kelly. Scott spent a year on the International Space Station, while Mark stayed on Earth. When Scott returned, he had aged about 8.6 milliseconds less than his twin brother. It's a tiny effect because the ISS doesn't go that fast, but it's real. Scott Kelly literally time traveled into the future by almost 9 milliseconds. This is not science fiction. This is our universe. Time is flexible. Time depends on motion. And if you want to travel to the future, all you have to do is move really, really fast and come back. So what have we learned? Time is not absolute. Time is not the same for everyone. Time is a dimension you move through, and the path you take determines how much time you experience. The twin paradox isn't really a paradox at all. It's a feature of space-time geometry. Different paths have different lengths. The traveling twin takes a shorter path through time. Simple. But the implications are staggering. Einstein figured this out in 1905 with nothing but thought experiments and mathematics. He dismantled thousands of years of assumptions about the nature of reality. He showed us that our intuitions about time are fundamentally wrong. And this is just special relativity motion at constant velocity. When Einstein added acceleration and gravity into the mix with general relativity in 1915, things got even weirder. Gravity slows time. The stronger the gravity, the slower the clock. Near a black hole, time nearly stops. We live in a universe where time is flexible, where the future is relative, where your clock and my clock don't have to agree. That's not confusing. That's not a problem. That's beautiful. That's one of the most elegant truths about reality ever discovered. Einstein didn't just solve a paradox. He revealed the true nature of time itself. And that, my friends, is why Einstein was a genius